this energy is always in the cell because always I need energy to break a bond. It couldn't be that the bond gonna be spontaneously gonna be broken into pieces. Now I have here here those examples: HH bond, CC bond, C double bond, C triple bond, C. So the bond order for each one of those. So the hydrogen-hydrogen bond order is 1, carbon-carbon because it's a single bond. If the bond order is 1, for C double bond, C, it's a 2. The bond order is 2 because we have a double bond. For C triple bond C, the bond order is 3. The bond order of nitrogen is 3. If we look to the relationship between the bond dissociation energy and the bond order, as the bond order increases, the dissociation energy is increasing, and that definitely makes sense because definitely to break a triple bond, I need more energy than breaking a single bond or a double bond. So as the bond order increase, the dissociation energy gonna increase. And as we learned on Wednesday, that as the bond order increase, the length of the bond gonna decrease. Okay, so this is the greater the bond order, the higher the bond strength, and the shorter the bond is. Okay? Now, on OWL, you're going to find the table. I'm just going to walk you through this table, but before I go any further, if we look to the numbers of C double bond C compared to C single bond C, we find that the amount is not double. That means if I want to break a single bond, if I want to break a double bond, it's not double the energy that I need to break a single bond. And we're going to learn today that the second bond, which is the second bond, which we're going to call pi bond, is usually weaker than a single bond. And this is why the energy is not double. When we have a double bond and compared a triple bond is not triple the energy that I need for a single bond, because those bonds don't have the same energy, don't have the same strength. But definitely as the bond order increase, the strength of the total 3 bonds to break the 3 bonds is going to be high. So usually when you're on OWL, you're going to find a table like this. I'm just going to walk you what is this table about. So this table is giving you the bond dissociation energy, or the amount of energy you need to break a bond. The way that is here, if you have an H, single bond H, this is the energy. If you have an oxygen, let's say, an oxygen, single bond oxygen, this is the energy. For double, triple, and all double, triple bonds, it's going to be in the multiple bond part of the table. So the way that you can read that is by taking this and that, and I'm just walking you through it because before some students had problem reading this table on OWL or figuring out how to figure out how much is the energy. Sorry. How much is the energy, the dissociation, the bond dissociation energy. Okay, so let's go and I click it on this. Stop it at 1 step. So I'm going to stop it right here and check what you think, guys. And I have A to be 69%. A is the right answer. So the way that you have to handle such kind of questions is the first thing, draw the Lewis structure, because the strength and the length depend whether it is a double bond, triple bond, single bond. So from just looking to the molecules, it's hard to predict. You need to draw the Lewis structure. So this is the Lewis structure of the nitrogen. This is the oxygen. And this is for, okay? So the bond order for this is 3. The bond order of the oxygen is 2 and 1 for the fluorine. We know as the bond order increase, the strength of the bond is the highest. So this is gonna have the highest or the strongest bond. That means highest bond dissociation energy. While the one with the lowest bond order is gonna be the longest. So this is gonna be the longest bond. And definitely this is the shortest, which make A is the right answer because 1 is the strongest and 3, which is F2, is the longest. Okay, and this is the last slide that is included in our exam. Whatever I'm gonna talk about from now on is not included in exam 3. Okay, so we learned before that that we can calculate in chapter 5. If you recall, we calculate the delta H, which is the enthalpy of any reaction, either by doing Hess's law, which all of you learned. 3 equations or 3 reactions, we rearrange them so that when we add them together, they end up to the same equation, reactions that I'm talking about. Or by using the delta H formation, which is the delta H of any reaction equals the sum of the delta H of the products minus the reactant. There is a third way, and we're gonna learn it in this one, which is we can calculate the delta H, the enthalpy of any reaction, by taking into consideration the energy required to break the bonds and form the bond. And it is written right here. It's the delta HR, the energy required to break bonds, minus the energy evolves when the bonds are formed. So mainly the delta H of reaction is the sum of the delta H of bonds formed, bonds broken, minus the sum of the delta H of the bonds formed. And we're gonna do an example and some eye clickers on those. Okay, so we're gonna start with our first example, which is I have this reaction, H2 plus Cl2 to give 2HCl, and the aim of this is to calculate the delta HR of this reaction. I know I go to the tables and I pick the bond energy for each one of those. Now the way to handle this is first to write the Lewis structure of each of the reactants and the products, because from looking at it you don't know if there is a double bond, a single bond, how many bonds. So the first thing is to draw the Lewis structure of that. I know that this is the Lewis structure of H2, this is the Lewis structure of Cl2, and my next step is to figure out what are the bonds broken and the bonds formed. So I'm gonna start with the bonds broken. So I compare both of those. Clearly this HH bond is broken for that HCl to be formed. So first H, and I have only one bond of that broken because I have only one H2. Then definitely that Cl-Cl bond is broken for this to be formed. So one Cl-Cl bond is broken. Now the bonds formed, clearly 2 HCl bonds are formed. Now I go to the equation, which is delta HR is the sum of delta H bonds broken, minus the sum of delta H bonds formed. So delta RH equal the delta H of H plus that of delta HCl minus 2 the delta H of HCl. Now I have to plug in the numbers. So delta HH is 436 kilojoule per mole plus the ClCl 242 kilojoule per mole. And definitely all of them are pluses because it is an endothermic, because you need energy to break a bond. And the answer of that would be minus 186 kilojoule. So this is the alternative of Hess's law or the delta H formation. This is another method. So we have for now 3 methods that we learned during this course of how to calculate the enthalpy of reaction. Okay, so let's do kind of eye clickers just to make sure that you get the idea and for you to practice. I'm just going to give you a couple of seconds to write down. I see some of you are still writing. Okay. Calculate the enthalpy change for the reaction below. So maybe you're going to calculate the delta H of this reaction, knowing those. Okay, I'm going to stop it at 2 minutes. Okay, so I'm going to stop it right here and check what you think. And I have for B 51%. So let's see. So first of all, I would do the Lewis structure for the reactants and the product just to make sure that it is single bond, it's not a double bond, and all of these stuff. Two. This is the Lewis structure. So the bonds are broken. Clearly, one BR bond is broken. 3 FF bonds are broken. So those are the broken ones. Now for this case, I have definitely 3 fluorines, 3 BR fluorines are formed, but I have 2 of those, so it's going to be 2 times 3, because I have 3 bonds, BRF, and those are the stoichiometry is 2. So it's 2 times 3. So the delta H of this reaction equals the delta H of BR plus 3 the delta H of FF minus 6 the delta H of BRF. And that's going to end me up with, for the BR, it's 193, definitely kilojoule per mole, plus 3, 155 kilojoule per mole, minus 6, 249 kilojoule per mole, and that's going to end up us with it. Okay. So let's go a little bit higher level and that kind of question. Till now, it's still like simple. So all what you have to take into consideration, the bonds that are broken, what are they multiplied, the stoichiometry in them. So let's go a higher level and do the next one. So here are your choices. So using the bond energy, calculate the approximate enthalpy of the reaction, of this reaction, which is a combustion reaction. We did this reaction using Hess's law. We did calculate it using Hess's law. Now we're gonna do it using this one. I'm going to stop it at 3 minutes so that you get the chance to do the calculations. Okay, so I'm going to stop it right here and check what you Okay, and I have 51% for B. B is the right answer. So what I'm gonna do is I'm gonna insert in here. So first of all, I'm gonna write the Lewis structure. For each one of those. Okay, the bond broken, clearly those C4, the 4 CH bonds in the methane are broken for the HO bonds to be formed. Clearly the 2 double bond oxygens are broken. Now form, I have 2 OH bonds that are formed, but I have a stoichiometry of 2, so it's going to be 2 times 2 OH. I have 2 CO bonds that are formed. Now the delta H, and I'm going to write it in here so the delta H of this reaction is the delta H for the delta H of CH plus 2 the delta H of O, double bond O, minus 4 the delta H of OH, minus, because the minus is for the sum of all the bonds formed, minus 2 the delta H of C double bond. So the delta H equal 4 times CH, which is 413 kilojoule per mole, plus 2 O double bond oxygen, 498 kilojoule per mole, minus 4 OH, which is 463 kilojoule per mole, minus 2 C double bond O, which is 695, and the delta H is minus 594 kilojoule. So this is how we handle the bond dissociation energy. I think that's the last I click here about the bond dissociation energy. Let me just check that. Yes. Okay, so by this we've done from the bond dissociation energy and how we use it to calculate the enthalpy of reaction. Now what I'm gonna do now is I'm gonna go over some Lewis structure of organic compound out and how you can handle them. Okay? And I'm gonna start with something like C2H6. And because all of what we've done before is inorganic compound like sulfate, nitrate, chloride, hypochlorous acid, acids, bases, but we never touched base on how to handle organic compounds, and mainly hydrocarbons. And I mean by hydrocarbons, those compounds that are composed of carbon and hydrogen. Usually we have all hydrocarbons are carbon and hydrogen with different proportions of X and Y. Okay? Now the first example of that, and usually we have 3 classes of hydrocarbons. The first class is called alkane, which have the formula of CnH2n plus 2. In other words, that the number of carbons gonna be double plus 2 the number of hydrogen. The number of hydrogen gonna be double the number of carbons plus 2. And in such kind of compounds, all in the whole compound, it's all single bonds. And we call this alkane. The second one is alkene, and the formula is CnH2n. So the number of hydrogen is exactly double the number of carbons. And in that, we have double bond in that compound. And the last one is alkyne, which the formula is CnH2n minus 2. We have a triple bond in that compound. Okay, Now let's recall for carbon. Carbon, from all what we learned during Lewis structure, when we handled Lewis structure, is going to have 4 bonds. It can do double bond and triple bond. It's going to have 4 bonds. It's going to have the octet rule. It never disobeys the octet rule. We know that hydrogen always going to make 1 bond. Okay? So we know carbon needs 4 bonds, hydrogen 1 bond, oxygen 2 bonds. This is what we learned, and definitely a lone pair in there. So the way that we handle those when we're drawing the Lewis structure, you can definitely go back to the long method that I taught you, but usually those organic compounds, there is an easier method to do that. So first of all, figure it out. Is it an alkane, alkene, or alkyne? Clearly this is an alkane, right? And that should be, yes, 2, because n equal 2. So 2 times 2 plus 2 equal to 6. So that's an alkane. So all the bonds going to be single there. So I have 1 carbon. I'm going to connect it to the second carbon, because hydrogen can never be the central atom. It cannot be in the middle. So I'm going to connect the carbon to the carbon, and then definitely I'm going to do it. I have no other choice but to do it in a symmetrical way in this case, which is this going to connect it to hydrogen, hydrogen, hydrogen. Now this carbon have 4 bonds, octet rule. Then I still have 3 hydrogens to go. 1, 2, 3. I have 6. 1, 2, 3. Definitely you can use the other method, but this is definitely when you go to the Orgo course, you're not gonna sit and do the long method. You're gonna just know that, okay, carbon gonna have 4 bonds, hydrogen 1 bond, gonna make 1 bond. So this is usually C2H6 is also written in this formula, CH3, CH3, and when it is written this way, it means that those 3 hydrogens are connected to this carbon, and this carbon is connected to the carbon next to it, and those 3 hydrogens correspond to this carbon. This is what it means when the formula is written this way. Okay? So this is when we, for the alkane, we're gonna do another example of also organic compounds, which is this one. How would you handle something like this? First, the way that it is written, as I put it in here, it's telling you that those 3 hydrogen are connected to this, this is to that, this is to that, and this hydrogen is connected to the oxygen. Okay? So it's kind of self-explanatory how to draw that. All what you have to do is to make sure that each one of those gonna have the octet rule. When we look to the oxygen, it doesn't have the octet rule, so we add those 2 lone pairs. Or what you can do is you can connect it as it is. You can do the other method is to connect it as it said in there, that the 3 hydrogen are connected to the carbon, the 2 hydrogen to the carbon, the 2 hydrogens to the carbon, oxygen to the hydrogen, then calculate the total number of valence electrons, which is going to be 3 times 4 because I have 4 carbons, plus 6 because I have total of 6. And then I have oxygen 6, and I have 8 hydrogens, so those 4 hydrogen, 4 H's, this is 4 oxygen, that's a total of 26. Minus 22 electrons in bonding, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Times 2, because each bond represents 2 electrons, and I'm left with 4 electrons. All the atom has the octet rule, so I'm obliged to put those 2 electrons on the oxygen because it does not have the octet rule. Now, if I put the condensed formula of this compound, that means I make it all together like 1, 2, 3. So C3H8O. If I give you that formula, that corresponds to this one and to some other Lewis structures. Usually for organic compound, Most of them, they don't have only one Lewis structure. They correspond to what we call structural isomers. That means geometrical isomers that they have the same molecular formula but different arrangement, different geometry. But for this one, as it is written in here, this is the way that you can handle it. We're gonna do one more, which is C4H10. First of all, is that alkane, alkene, or alkyne? It's an alkane because I have n equal to 2 times 4, which is n, plus 2 equal to 10. So that's an alkane. I know for sure that all the bonds gonna be single. The way that I'm gonna do it, this one has 2 Lewis structure. So the first one, I'm gonna connect the carbons in a linear way. So I'm gonna do it all the carbons in a straight line. Then I'm gonna begin adding the hydrogen so that I fulfill the octet rule for each carbon. So this has 1, so it needs 3. That has 2, it needs 2, 2, 3. Now, before I say this is the Lewis structure, I double check the number of hydrogens and the carbons. So I have 4 carbons, 3, 3, 6, 7, 8, 9, 10. So that's a right Lewis structure for C4H10. But it's not the only Lewis structure. So I assume that, okay, let's put all the carbons, let's connect them in a straight line. The other Lewis structure, and both of them are right, is to put the 3 carbons in as a main, and then I put the other carbon in here. Then I take the hydrogen and I begin adding the hydrogen to fulfill the octet rule. So around each hydrogen should be 4 bonds, 4 bonds, 4 bonds, 4 bonds around each carbon. So the total is C4H10. So both of these are the right Lewis structures for C4H10. Now, if I have n being higher, like C6, we're gonna have more Lewis structures. So it depends how. Because if I keep moving, if I move this carbon and put it here, I'm gonna go back to the linear chain. So it depends as the number of the number of carbons increases, there will be more Lewis structure, which all are like, but the relationship between each other are geometric. They are geometric isomers. That means they have exactly the same molecular formula, but different geometry. And this is why we talk about the Lewis structure of organic compounds at the end of this chapter, because it's different than when we talk about inorganic compounds. Okay, let's do one more. So this is formic acid. So what did we learn about all acids? What is special about all oxo acids? And this is one of them because it's oxo and it is an organic acid. What did we learn about them? So the special about acids when I'm writing the Lewis structure is that I connect the hydrogen to the oxygen. So when I'm connecting, I connect the hydrogen to the oxygen. Then I'm going to put the carbon as a central atom because it's the one with the lowest electronegativity in this case. And I'm going to connect this. And so. Now my next step is to calculate the N total, which is somewhere in here. So the N total, I have carbon belongs to group 4, 2 times 6 oxygen plus 2 hydrogens. Hydrogen, oxygen, and that's for the carbon. That's a total of 18 electrons. I have 4 bonds minus 8 electrons. It's going to end me to 10 electrons. So I'm going to put 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So that's 6, 7, 8, 9, 10. Then I'm gonna look to the carbon, and the carbon does not have the octet rule. So what I'm gonna do is I'm gonna borrow those 2 electrons, and this is the Lewis structure of formic acid. Now, it may come to your mind, okay, why she didn't connect the second hydrogen to this oxygen? If I do so, and I calculate the formula charges that we learned about on Wednesday, I'm gonna find that that structure is not the most favored structure, because the formula charges on the atoms inside that arrangement is not closest to 0. So we learned on Wednesday that after I write any Lewis structure, I'm going to calculate the formula charges. And if the formula charges are inside the atom, a Lewis structure is closest to 0, that's the most favored Lewis structure. And if I do the other arrangements, it's not going to be the most favored. This is how I know that this one is the favored one. So in other words, if you have 2 Lewis structure and you want to know which one is the right one, you do the formal charges. You calculate the formal charges of each atom inside that Lewis structure, and from there you can figure out which one is the right one and which one that you're going to use when you're writing compounds or using it. Now, and that will be the last thing on chapter 8. We're going to start today with chapter 9, which we're going to talk about bonding. So in all our talk before, we talked about atoms, we talked about the electronic configurations of atoms, and we said, oh, some they lose electrons, some they gain electrons, and things like that, but we never talked when they combine together, when this H and H combine together, what they're gonna form. We know that they're gonna form a bond, but how does this bond look like? We talked in chapter 6 about when we were talking about Schrodinger's and about the subshells being SPD. We talked about the shapes of those atomic subshells. But what about the molecular shells? How would the molecular orbitals look like? And when I say molecular orbitals, I mean in a molecule. That means a compound. So we're gonna start looking at those. So we're going to start with a hydrogen with an H2. So we have 2 theories. When we talk about bonding, there are 2 big theories out there in chemistry. One is called the valence bond theory, and the other one is called the molecular orbital theory. Usually they are used in parallel because usually one of them would fail to explain a phenomena, then we use the other, and they are kind of complementary to each other rather than opposite or conflicting with each other. So this is why I'm going to teach you both the valence bond theory and the molecular bond theory. And usually they are used in parallel. As you go to any chemistry course, you're going to hear about both. So I'm going to start with H2. So we learned at the beginning in chapter 7 that the electronic configuration of H1 as an atom is 1s1. So here I have and 1s1. So I have 2 hydrogen atoms. So when they're gonna come and combine, both of them, they have an s orbital, right? Because it's an s subshell. When those 2 s subshell combine together, this 1s and 1s combine together, those electrons, one of those electrons should be opposite to the other. So even if it is up, it's going to go down inside so that they can form this bond. And they're going to form what we call the molecular orbital, and that molecular orbital is called the sigma bond. Now the sigma bond is a combination of an s and s. It can be also an s and p. But in this case, it is 1s with 1s, and this is the shape of the orbital that is going to give, and it's called a sigma bond. Okay? And that represents the bond in here, which is a single bond, and this single bond is called a sigma bond. So in other words, any time a 1s combines with a 1s, which are both of them, we learned that the highest probability for an electron in a 1s in a spherical, and the other one in a spherical around the nucleus, when they combine with each other, they form that kind of two cylinders combined with each other with zero knots. There is no knot. This is only the nucleus. Definitely the electron is not gonna crash the nucleus, because if it does so, it's not an electron anymore, because it's gonna combine with the protons. So the sigma in here is a combination of 1s and 1s, and it has a zero. Now what if I have HF? What about the bond in HF? So I know that H is 1s1 as electronic configuration, and I know fluorine is 9, and I'm gonna write it in the opposite way so it's closer to this. 1s2, 2s2, 2p5. 2p5. So in this case, I have, this is the fluorine, this is the hydrogen. The hydrogen needs 1 electron and the fluorine needs 1 electron. So what's going to happen that the electron, that subshell S and that subshell P, they're going to combine with each other also to form a single bond, because we know that HF going to also form a single bond. So that single bond is also called a sigma bond. In other words, every single bond is a sigma bond. So when 1s combines with 2p, which we learned that this is kind of the shape of a 2p, they form, then one electron is going to be opposite to the other, and they're going to form this sigma, but since it is between 1s and the 2p, it's going to have one node, which is right there. And this is what we call the sigma bond. This is how we describe. So in other words, the electrons between H and F is gonna have, this is the highest probability to find an electron is in that kind of shape, between those two H and F. And this shape, which is the sigma bond that we talk about. Because again, we said that the electron is not in one place, it's kind of, and we say it's in a subshell S or in a subshell P, but in real life, it's the highest probability to find the electron in there. And this is the highest probability to find the electron in the molecule HF. Now, what about if I have the nitrogen? So nitrogen is 7, so 1s2, 2s2, 2p3, and the other nitrogen, because this is N2, so the other nitrogen also is going to have 2p3, and it's going to have, okay? So the first thing that's going to happen, that this electron gonna combine with this, so this P and this B gonna combine to form a bond. So this is our first bond, this is the second bond, and this is the third bond. So this is the representation of the very first px with px. So now I'm combining px with px. When this nitrogen gets close, this px and px, we have the electron, and they combine to form the sigma bond, which have now two nodes. So between 1s and 1s, there is 0 node sigma bond. Between S and P, there is 1 node in the sigma bond, while if I have a P with a P combining together, they form a sigma bond but with 2 nodes. This is only described the first bond between the nitrogen and the nitrogen. It's this bond, and it is a single bond, This is why it is called a sigma bond. Now, when the other P and this P combine, they form a pi bond. And this is the second bond in the nitrogen, and it looks definitely different than the sigma in its shape, because the sigma looks more like cylinders next to each other. This is the two cylinders above each other with the nodes in between. Now, without this. So usually a pi bond, this is kind of a representation. This is the single bond, and this is a pi bond in there. So the pi bond is kind of perpendicular to the molecule. So this is the first pi bond. Then the second, when we have, this is P, when we have the last P with this last P, is going to form another pi. And this is how would the molecule look like without those white stuff out there. Okay? So this is how molecules form bonding, or how would the molecular bonds look like, according to the valence bond theory. And those are the three bonds that are formed. So mainly when 1s and 1s combine, they form a sigma with no nodes. I'm going to go back, just because the material is harder than anything we talked about. So then we have, when we have 1s and P together, they're going to form also a sigma bond, which is a single bond with a node in there. When we have a P with a P, the first, if we have 3 electrons that are unpaired, they're going to pair with the electrons which are also unpaired. So for a bond to happen, you need an unpaired electron in different orbitals. And I'm going to stop right here, and I'll see you Wednesday at 7 p.m.